Like it is a property, alpha or the chemical potential is a property of temperature. When the temperature is 0, means 0 Kelvin, not degree centigrade, 0 Kelvin, the absolute temperature, then this is equal to the Fermi energy. And you know the Fermi energy. The Fermi energy is the topmost field level energy at 0 Kelvin. So at 0 Kelvin, the Fermi energy is actually the chemical potential. Right? So it is that energy which is at 0 Kelvin. And now let me just talk about the different, you can say, aspects of these distributions. We will not talk about those limits from the Fermi-Dirac or from the Bose-Einstein statistic, we go back to the Maxwell-Boltzmann distribution. That comes under the laws of thermodynamics, and that derivation is under thermodynamics. But here we will just discuss some limiting cases regarding them. Okay, so look here. First we look at the Fermi-Dirac distribution. And the Fermi-Dirac distribution gives you what? Look here. The Fermi-Dirac distribution, any is equal by putting these values, like putting beta equal to 1 over kBt and alpha equal to minus mu of T and kBt, putting these values and replacing the En by just E here, because it will then vary for the 0 temperature and the Fermi level temperature or whatever it is. So it will become e to the power minus and mu of T divided by kBt plus, and this is 1 over kBt and En. This is positive, this is negative. So I can write this one is 1 over e to the power E minus mu. Right? Because this is energy, no E, and I write in terms of this tilted E and minus mu and whole divided by kBt. I can write it as kT because k here is the Boltzmann constant and plus 1 here. Right? And similarly, I will put in all of them these values. Now look here. When let's discuss some approximations. When T goes to 0, like here T goes to 0, then something divided by 0 is infinite, and e to the power 0, e to the power infinite becomes again infinite. Okay, then 1 over infinite is 0. So it means when T goes to 0, N of E goes to 0. But let me do this thing in steps. And in steps I can do it like this. When T goes to 0, what about e to the power E minus mu over kT? What about this one? It will go to 0, then it depends. It will go to 0 when E is less than mu. Right? When E is less than mu. Because it will be 1 over this one. And it will go to infinity when E is greater than mu. This is again another thing in it. Because when this one is less than mu, then it's a negative number. And negative will further, you can move it down in order to make it positive. So in this situation, this whole term will go to 0 if this is negative. This is negative. And if this is positive, then what we discussed earlier, that it will go to infinity. This is another condition in it. And what about the Ne? What about Ne when T goes to 0? So Ne, it will go to 1. It will go to 1 under this condition, when energy is less than the chemical potential. Because in that situation it will become 0, right? So this whole term will be 0 plus 1. So 1 over 0 plus 1. So it will go to 1. And it will go to 0 if energy is greater than mu. Right? So the maximum when T goes to 0, then it depends on these two. But if we don't consider even this condition, then when T goes to 0, then Ne either goes to 1 or Ne goes to 0. Like we are having the two values for the T going to 0 case, means when you are decreasing the temperature of the system, then what will happen to the fermions which are following the Fermi-Dirac statistics? Okay, let me explain a little bit about them as well. But for the while we will do this one and then we will explain this one as well. That like Maxwell-Boltzmann distribution. The Maxwell-Boltzmann distribution is for the classical particles, distinguishable particles. Their number and the density of states are having no quantum mechanical effects. And this distribution is only applied to the classical particles, for example, the gas molecules of the gas. You have applied some laws like Chance law, Boyle's law and all those. So this distribution only applies to that. It's a classical thing. While the BE and the FD distribution are purely quantum mechanical. For the FD, you know that Fermi-Dirac distribution, they are fermions. Fermions means they are half integral spin particles. Half integral spin means they are either electron, protons or neutrons. You can go to some atoms as well in helium-3. Helium-3 is also a fermion. We have discussed the helium-3 as well. So it's also a fermion. Half integral spin. When means for the half integral spin we are having the Fermi-Dirac distribution, and these particles are following the Pauli exclusion principle. One particle per one state. No two particles in one state. You know that thing, the Pauli exclusion principle we have applied to the Fermi-Dirac statistics. While this one, the Bose-Einstein distribution, this is also for quantum mechanical particles. But these quantum mechanical particles, they are not obeying Pauli exclusion principle. So there can be more than one particle per one state. Right? And further, these states, these particles, they are integral spin particles. Integral are zero spin particles, like we are having the photons, we are having the bosons, we are having the helium-4, like helium atom. Helium-4 is helium atom. Helium atom is a boson. Okay, it is having integral spin. It is not having half integer spin. So these are different sorts of particles, and they follow different kind of distribution. You cannot apply Bose-Einstein condensation on the electrons because they are not following it. We have already calculated the ground state energy in case of the fermions, that it was quite high compared to the bosons. So bosons apply to the photons, helium-4 means the helium atom, they are bosons. And while the Fermi-Dirac statistic on half integral particles. Okay, this one is fine that these limitations are there. And now what about another limitation? Now if I do plot all these distributions, and let me go like this, that we are having one of the figure of your book, and that figure is this one, that you are having N of on this axis you are having E, means the energy, and on this axis you are having Ne. And now here, this is a value, let's say 0, means the origin, this value is 1, this value is 2. And now look at this distribution. When E is equal to mu, right? When E is equal to mu, what is that situation? When E and mu are the same, then that is the Fermi level situation. The most occupied, or the utmost level which will be occupied, will have its energy equal to the Fermi energy of the system, and it will be the T equal to 0 situation, right? It is the T, the absolute 0 situation. And let's say this is that value of E, where E is equal to EF. Then you know that what will be, like it should be, when it is a T equal to 0 situation, like here, there are, you can say the Ne value is 1, and it is here, and as it crosses the EF, it falls down quickly to this value. And this I call is the T equals to 0 situation. And when you just put this limit at equal to EF, then at equal to EF, when this E is equal to mu, then this is equal to 0. And for any other T is non-zero, then this term comes out to be E equal to 0. You just understand this one. This is important. When T is 0, then E is equal to mu. So 0 by 0, it is undefined. Okay? Means it is infinite. And infinite means again we will have all these things and it goes to 1. When this is a situation, E is greater than mu, it goes to 1 and it is here. And when E is equal to EF, then it automatically falls to 0. Right? Very quickly it falls to 0. When you say that E is greater than this one, but T is non-zero, there is some temperature. So what will be in that situation? E to the power 0 by T. So it means it is E to the power 0. E to the power 0 is 1. 1 by 1 plus 1. So it comes out to be half, 1 over 2. So this is a half value. This is half value because this is 0 value. So this will be just like this one, that it is the half value and the distribution will go like this, coming from 1 and crossing this one and going to 0 as E increases. Right? So it will go like this one. Now if I want to plot the other distributions, like let me plot the Maxwell distribution first. Now look at the Maxwell distribution. When you will write the Maxwell and the energy density form like this, like the density of state, it will be E minus mu by kT. There will be no plus 1 or minus 1 here. Now what will be in this situation? When E is equal to mu, then this will become 0 and it will become 1. Right? Means 1 over e to the power 0 is 1. Look here. 1 e to the power 0 and it comes out to be 1. So its starting point is from here. The Maxwell distribution will start from here and it will go and join this one. So it will go like this. Means it is exponential decay and it will go like this. Right? What about the other distribution? It is 1 minus 1 means when e to the power 0 is here and this is minus 1. Like here we are having minus 1. When this become 1, then it is 1 minus 1. So 1 over 0 is undefined. So it will not start from here, but it will start from somewhere here because this value is undefined for it. And it will start somewhere from here and it will go with this and will go to 0. When on the maximum values means the density of states will fall because this is n of e. So if I want to make it complete, then it will be something like this. And some values here, then here. So this is 2, this is the 0 value, and I can have some minus value here because on this side, let's say this is our 0 value and this is our minus 2, minus 4, and this is minus 6 value on the x-axis. Y-axis is 0 here. While here is plus 2 value and plus 4 value and plus 6 value. Right? So when this number is increasing, then we will have some distribution here like the Boltzmann starting from here. The Bose-Einstein. This is the Bose-Einstein. While the Maxwell will start from here and it will cross here at 1. And this one will start from 1 and it will go along this and then fall to this one. So for the limiting cases, when the number when any will be very, very less, or when the temperature will be very, very greater, like kBT will be very, very greater, then the Bose-Einstein and the Fermi-Dirac statistic both will go to the Maxwell statistics, to the classical particles. Like we know that our electrons or our bosons are in particular states. But here we don't have any particular states. Here they are randomly oriented. They are classical particles. There is no quantization of states. And as you know that when you are rising electron inside an atom, you reach a continuum. You reach continuity. Here is continuity. In these two there is quantization. But when you increase these two conditions, like Ne is very, very less. The number of particles are now very, very less. Like particles are so far apart each other that their interaction wavelength is much, much less than the de Broglie wavelength. And then we will say they are non-interacting particles. They are now classical particles. They are no more quantum mechanical particles. So in your book, only this one has been discussed like this, and this here, it falls quickly here. At any other temperature, like this one is at T equal to 0 and this one is at T greater than 0. But if you want to see the other distributions as well, then their distributions will be like this. Okay? Thank you.